So this is called as the singular value decomposition and MIMO capacity. Now, what exactly is meant by it? That when we are doing SVD, as I told you, that this is basically a tool which makes sure that we decompose a complex wireless channel into simpler decomposed outcomes, which is U, sigma, and V transpose, or V Hermitian for that matter, and we can extract many information out of it. Similarly, one of the very important factor that comes across from SVD is, as you can see over here, one of the application of SVDs is to optimize the power allocation in a MIMO channel scenario. All right. So we have a scenario. Let's visualize something like this. Maybe that we have input power. So there are multiple channels, as we know from my MIMO system. There can be multiple parallel channels, and that is one of the advantage of having a MIMO system. Now, if you observe over here, that P1s are the input channel input power which we are feeding in, and we are getting an output power which are primarily an alpha to that of P1. Where these alphas, as you can see, alpha 1, alpha 2 up to alpha n, are nothing but the channel gain. Now, this can be additive, or like it can amplify or boost the signal, or it can deteriorate the signal also, whatever it is. The point over here is that how we can optimize the power allocation to all these n parallel channels. That can be extracted from the SVDs based on certain rules. Okay, so today's discussion is primarily that how we can optimize the power across n such channels, and secondly, based on that, what can be the maximum MIMO capacity, which is nothing but the Shannon's capacity theorem, which we all know. But there we are going to apply this n parallel channels. Alright, so again, in this, there are a lot of complex derivations which are there, which we are going to opt out again, but we are only going to focus on specific areas, and we are going to solve specific numericals so that we are able to solve them. So the first thing that comes in across is that you can see this is the same equation which we have already are familiar with, y equals to hx plus n. So that instead of h, we are writing it as in terms of the channel gain over here. So we are looking at the square root alpha 1. Now this is very important. Please make a note of it. Is that you can see here I have mentioned this square root alpha I, or the channel gain, is nothing but the values which we can get it from the singular values from the sigma plot. If you remember the sigma array which you have done recently for your CAT, I guess you already are familiar with. So sigma 0, 0, sigma 2, like this, if you are having this. So this sigma values that you are looking at, okay, so the alpha, square root alpha, so ideally the value of sigma 1, suppose I consider as alpha, so sigma square is nothing but alpha 1, and sigma 2 square is nothing but alpha 2, like that. Okay, so the channel gains can be inferred quite easily from the decomposed sigma array. Alright, so now this value or the elements on this matrix can be found out in the same manner as we have done with the eigenvalue calculation. So same process goes. After that, suppose you have decomposed it into U, sigma and V. So from the sigma array, the values that you are getting in, if you square them, you will get the channel gain. That is the only thing that is important. Okay, so we'll see that with numerical later. So that is all it is. Now, if I consider this as a scenario, yi equals square root alpha I, xi and ni, where ni is the noise, and we go on with the SNR calculation. Now, SNR will not have pi only, but it will also have a output which is alpha I pi, because the channel gain is what we are including in our calculation as well. So alpha I and sigma square, and this is my SNR I. Alright, now we have to calculate the maximum rate. Now, as you know from Shannon's limit capacity theorem, we know that the rate of it is equal to nothing but log of 1 plus SNR. So the same thing we are looking at. So rate is equal to 1 plus log of SNR, which you have, I think many of you, those who have done ITC, or at least almost of you have done the ITC, you have seen that this is basically a limiting condition, that what will be the maximum rate at which we can send the data, given that the channel capacity is less than the rate. So like that, if it is within the capacity, that is the maximum rate at which the data can be transmitted. So same way, the same formula we have written, R equals to log of 1 plus SNR, where SNR is nothing but alpha I by sigma square. Alright, and if I consider this to be over the entire n possible outcomes or n possible channels, so maximum sum rate or the total sum rate is nothing but, this is a new term actually, sum rate across all the parallel channels is given by S max is equal to maximizing the capacity. What is the maximum rate at which we can? This is the rate. This is the rate across each channel, and this is the maximum rate which is possible for the particular outcome. Right. So this is basically these two equations. Make a note, but I don't think it will be required that much. But primarily, this will be useful later on when we calculate the MIMO capacity. But you will understand this application of this later and not right now. Okay. So these are the two very important equations with respect to the capacity. So we are trying to find out what should be the maximum MIMO capacity given that we know about alpha. So if you can solve this quite easily, if you know about this Pi, see this equation very carefully, you can understand, you can get this value of maxima if you know about Pi, the power allotted for individual Pi. What is Pi? Pi is nothing but the power allocated for each and every n number of channels. So suppose there are 5 branches. So 1, 2, 3, 4, 5. Each branches will be allotted a specific optimized power. So that is basically given by that Pi. Now we will know that how do I calculate that Pi. And second part is alpha, which is coming from the singular value decomposed outcome, which is nothing but this. Yes, please. No, it can't be. It can't be. Each channel cannot have same power because each channel suffers different set of attenuations. So you cannot have a single uniformity across all the channels. For example, I'll just give a simple example. If suppose one channel is very poor in condition, there are lots of foliage and lots of interference in between. Naturally, the power deterioration will be much in those cases compared to some place where there is a line of sight, where there is no interference. So naturally, if you uniformly distribute the power, it doesn't make sense because the person which is not having much power, it will still not have much power because of the interference. So accordingly, there should be some optimization that needs to be taken place. That is where the convex optimization comes in. But we are not going into the details of it. We'll just touch upon some specific points of it. Now we come to that equation once again. So you can see here, this is very, very important. Please make a note of it. So you can see the maximum log of 1 plus alpha I by Pi is only valid. This is very important condition. Please make a note that if the summation of the Pi, that is the individual power as allotted across n possible branches, and the summation of it should be always be equal to the transmitted power. Transmitted power is a constant. How we are distributing the transmitted power or how much we are feeding is as a transmitted power is always constant. So whatever optimization we come across or how we are distributing across n number of channels, it doesn't matter, but overall the total summation cannot exceed the transmitted power, which is quite a reasonable approximation. And the second part is, which is also essentially important, we'll solve a numerical, you will understand why this is significant, is that Pi should always be greater than 0. Power cannot be negative. Negative power cannot be there. So that means when you are allocating a power, if during the calculation, you come across that Pi in any of the branches, suppose there are 3 branches, branch 1, 2, 3. Now suppose the third branch gives you a negative power allocation by calculation. Calculation I have not shown you, but suppose the allotment or the optimized power allocation shows that the third branch is having a negative power. As per the condition, that cannot be. So what you have to do is, for the negative power, if at all it's coming for any branch, we have to approximate that to the nearest value, which is 0. Understood? So for example, you have 1 branch, 2 branch and 3 branch. 1, 2 and 3. Now after calculation, you have got a positive power here, you got a positive power here, and you got a negative power here. So this is our P1, this is my P2 and this is my P3. Suppose after optimizing everything. But if this P3 is existing with a negative power, you cannot have a negative power. So what you have to do is, this negative should be removed, and the minimum thing that you can do is that you can put P3 equals to 0. That's all you can do. That means that out of the 3 branch, the third branch will not be given any power at all. It's a very faulty design, you might say, that if no power is available there, then what will happen to the SNR? Definitely that will be a faulty system or lossy capacity will be there. But that is how the allotment should be. Okay. So this condition, please make a note of it. This is very important leading to our discussion. Alright. So what we have observed till now, so we are trying to find out the MIMO channel capacity using the normal Shannon capacity theorem. But in order to do that, we need to take a hold of this Pi power. Now, this is not a very simple way of dealing with it, because how we are going to distribute this power across n number of branches depends on an optimization problem. So that is mentioned in the next part of it. So you can see that as 4 means this equation that you are looking at, this part, although it looks very simple and not that difficult as such, but the problem here is that it denotes an optimization problem. And that needs to be solved using the Lagrangian multiplier process, which is nothing but the basic of a convex optimization problem, which is, again, as I said, it's a different topic altogether. We don't need that as much. And based on that, what we are trying to do, basically, that you only understand that this is again a cost function. Cost function with a value of this Lagrangian multiplier is that delta. Okay. So please make a note of that value only. You don't need that this information as such. But what we are trying to achieve, you understand. What we are trying to achieve is we are trying to find out the optimized power allotment with respect to n number of branches. For that, we need to use this tool, Lagrangian multiplier method, in which we are trying to optimize the power. Okay. So in that, this is basically a cost function. So the cost function, like we have done for zero forcing, like we have done for MMSC, same manner, we are trying to establish a cost function and we are trying to make it happen so that we get an optimized result. Now to do that, you can see we need to maximize this cost function. This is a function that we are doing and the necessary calculation follows. We don't need that. We don't need that. The only thing that you need is that the final power allotment, Pi, please make a note of this, Pi is given by 1 by delta. This is very important because this we are not going to evaluate as such. So the power allotment Pi is given by 1 by delta minus sigma square by alpha I. Now alpha I, we know it from our SVD calculation. Sigma square is constant, which is a noise part of the channel itself. And we now find out, and this Pi, we can find out if we know about the 1 by delta. Okay, so the process is for all of these numericals, we will try to find out a way in which we can find out this 1 by delta. If we can get that 1 by delta, we can subtract it from sigma square by alpha I because that will be provided to us and we can find out what will be the allotment power. With numerical, it will be clearer, but for the time being, please make a note of this. So the point here is that from the given numerical or any channel, we'll try to find out this 1 by delta part. If I can get that, we can find out what is the optimized power. If I can get the optimized power, we'll go back to this previous equation over here, S, where we can substitute Pi, alpha I we already know, sigma square will definitely be given because it's a noise factor. We substitute everything and we can get the sum out. That is the basic objective. Alright. So let's see how we can solve the numericals then. So this is basically the same discussion going on for some time now. So let us just go ahead. So the significance of it. So let us just end up on this part of it. So significance of this. So you can see Pi is nothing but 1 by sigma. So this is for the overall generalized case. And this plus sign is a specific way of representation of a function. So that is that plus sign that you are looking at over here. Okay. So this is a total power constraint we call it. So we don't need to worry much. We don't need to worry much. The only thing that is important over here, you can see here, if alpha 1, alpha 2, alpha 3 like that, if it is alpha 1 is greater than alpha 2, if it is greater than alpha 3 and so on and so forth, what we mean is, this is very important because this is where the water filling concept comes in, that it means that alpha 1 is the strongest channel gain and alpha n has the weakest channel gain. Correct, everyone? This is the combination, okay? Because remember, alpha 1 is nothing but, what is alpha 1? Alpha 1 is nothing but 1 sigma square. Now in the sigma array, in the capital sigma array, if you remember, if I just go back over here, sigma 1, 0, 0, sigma 2 like this, in the condition was that this should be greater than sigma 2. So naturally my alpha 1 should be greater than alpha 2 and alpha 3 and so on and so forth. Now what is happening over here, you can see that if alpha I increases, that means the channel gain increases, definitely the ratio sigma square by alpha I decreases. Alright, which means eventually that the factor 1 minus delta minus this sigma I square, this also will increase because this part is decreased. Okay, as this will If this is decreasing, so this is equal to what? This is equal to Pi. So basically what it means is the last statement you can see, which means more power is allotted to the strongest channel. When this will decrease when factor of sigma square by alpha I will decrease only when alpha is reducing. Or rather alpha is increasing, alpha is increasing. Now when alpha is increasing, it means that that is the strongest channel. Because we have assumed that alpha I, the alpha 1 is the strongest channel and alpha n is the weakest channel. So if this portion, the portion that I have circled, if that is reducing, naturally my subtraction will increase. That means my Pi will increase for that particular channel, which means the final outcome you can see that the more power is allotted to the strongest channel. And the weakest channel will have the weakest power. That's all. So the concept is basically termed as the water filling process. Now what is water filling process? It's just a terminology. It's nothing very fancy about it. I'll just show you with an example, with a diagram of it like this. Okay, just understand this very easy diagram actually. So you can see this is my 1 by delta. Suppose we have found out the Lagrangian multiplier and this is my value. Now what is happening? You can see we have made these small blocks. Each of them are having sigma square by alpha 1. Now here, keeping in mind that alpha 1 is greater than alpha 2, alpha 2 is greater than alpha 3 and so on and so forth. So what is happening? See that this factor sigma square by alpha 1 is relatively smaller compared to sigma square alpha 2 and so on and so forth. So the remaining portion that you are looking at, so 1 minus sigma, what is this part? 1 minus delta minus sigma square by alpha 1 square. So this will be much bigger compared to the next one, and so on and so forth. So when you have a scenario of this last one, where we are considering that alpha n is the weakest, you don't need any power allocation for that matter, because it is beyond the level that you are setting it. So this concept is basically called as the water level filling. That means that from higher to lower it is, from lower to higher it is actually distributing its intent. It's basically indicating as if like a waterfall. So it's from higher to lower it is going on like this. So that is why it is called as water filling algorithm, nothing else. Yeah, that is the name of it. So the water filling algorithm is nothing but a process in which we are trying to allocate the maximum or the optimized power, I would say, to each n branches. And from those n branches, we are trying to find out what can be the maximum capacity of a MIMO system. Right? So that is basically the theoretical part of it. Now let's see with a question. Okay, let's see we can understand this very clearly. We don't need that much of information anyhow. But let's see with a question. See this understanding if you are able to do it. The question, this is 2 cross 2. We'll do a 3 cross 3 as well for this. Yeah, please. Alpha 1 will be greater than alpha 2. So this one like alpha 1, if it is smaller, then this portion that you are looking at, if alpha 1 is greater, how can this be greater? What you are saying is alpha 1 if it is smaller. Yes. This fact. Yeah, that's what. Yes, yeah. That's what I told you. Correct? So let's see a solving question. Please understand and focus on this question, because this you will be able to do it very simply if you follow the steps I told you. Suppose you are given an H matrix. This is very similar to the SVD question which we have done in our CAT 2 as well as the practice problem which we have done in class. You are given an H, okay, of any such values, and you can see the total power is given as P. That is PT is given as 4. In linear scale it is given. If sometime it might be given in dB also, you can convert that to linear scale also, or whatever it is. I have given it as 4. And sigma square, the noise part, this is basically the noise part, which is given in 3 dB, which I have converted to linear scale of 2. Now the question will come something like this: compute the MIMO capacity and optimal power allocated. Ideally, it may be only one question or maybe the two, whatever it is, 5 plus 5 will be the marking. Alright. See the process, because if you understand one process, it will be adopted for the others as well. Like you have done in your CAT 2 as well, I have seen that SVD, I told you that using the eigenvalue calculation, it will always give you the correct answer, and eventually U, V and the sigma will follow all the properties. Many of you have followed the same way. and everyone got it correct, in fact, by processing in the same manner, those who have done it correctly. So in that way, so the first step it is that you have to find the SVD. Okay, so the first step is to find SVD. As I mentioned over here, for the time being, I have not done the SVD calculation over here. It should be done in the same manner like we have done previously. Right? So that is the part of it. If you can intuitively do it, it's fine. Otherwise, you can follow the eigenvalue calculation and you will come across the U, the sigma, and the V transpose of the sigma. Okay. So I have kept it, I have just not done that part of it because that part only I have kept it for you to do it as if we have done the same way in the previous case. Now we are done with the SVD. Suppose this is what we have achieved. Now you can see what my alphas are. So you can see the sigma 1 is nothing but 2 square root 2, which is here, and my sigma 2 is nothing but square root 2. So my alpha 1 is nothing but square root of that. So we get a value of 8 and 2. Alright. What's that? So we have sigma 1 and 6. So we are getting the alpha 1. So what is alpha 1 and alpha 2? These are my gains. So these are my gains that we are getting. Follow the steps carefully and you will be able to solve them very easily. Alright. Now we have alpha 1 and alpha 2 done. So what next is the optimal power calculation. So this is my optimal power. So this is my equation which we know 1 by delta minus sigma square by alpha I. Okay? Alpha I we already know. Here there are two sets because it's R equals to 2. You can see here from the equation itself, R equals to 2 and T equals to 2 as well. So basically we have 2 cross 2 matrix, that's why. So Pi will have two sets, which is P1 and P2. Everyone clear with it? I is equal to 2 because there are only two set of antennas because R equals to 2 and T equals to receiver is 2 antennas, transmitter also 2 antennas. So there are two ways of dealing with it. So 2 antennas. So P1 and P2, two powers are allotted. Now you can see I have written down the same equation with alpha 1 and alpha 2. Now alpha 1 and alpha 2 is known to us. Sigma square is known to us. So that's what I have substituted over here. So we are getting a generalized outcome over here. Everyone clear with this? Sigma square is 2. Alpha 1 and alpha 2 is presented over here somewhere. So we have substituted over there and we got a generalized outcome of it. So P1 and P2. Now the second condition comes in. What was the second condition? That summation of Pi should always be equal to Pt. Transmitted power is constant. So whatever you allocate about P1 and P2, at least here as there are two only. So two powers should sum up to give you Pt. So that's exactly what we have done over here. P1 plus P2 is equal to P. Now instead of P1, P2, it can be 3 also. I'll show you the next question also, where there will be 3 set, P1, P2, P3 maybe. Right? So we have just substituted over here. Ignore everything what is present over here, whatever is present over here, even if right now, you just go on solving the value of 1 by delta. That's all we are doing here. I'm just skipping for the time being. We are just trying to find out what is 1 by delta. That's all. It's just a 2 addition equation. You can see here, it's 2 addition actually. So from that, you try to find out what is 1 by delta. Very simple. You get the value. Okay? Now, you take this value and substitute in P1 and P2 equation. What was the equation? 1 by delta minus 1, because you can see here the generalized equation we already have. 1 minus delta minus 1 by 4 and 1 minus delta by minus 1. So that is substituted over here. You can see 1 and 2. So we get two values of P2 and P1. And we convert that to dB scale. So now you can see the total summation will always be equal to 4 if you consider the linear value. And in terms of the condition that Pi should always be greater than 0, that also is satisfied. P1 is greater than 0, P2 is also greater than 0. So this is the condition. If that is not satisfied, your value of 1 by delta is not correct. Understood? In this case, while solving it, we found out that 1 by delta, we got the value as 21 by 8. Based on that, we found out P1 and P2 with some values. And they are giving us a result that P1 is greater than 0 and P2 is also greater than 0. So it satisfies the condition. Hence, we can say that the choice of 1 by delta, the Lagrangian multiplier, is actually correct. And these are two my optimal powers for the P1 branch or the branch 1 and branch 2. Now, if I know P1 and P2, we can find out, you can see here, it's mentioned here. If P1 and P2 will come as negatives, then we need to change the selection condition. We'll see that. Next question, we'll see that. That will also be there. So now we come to the MIMO capacity part. Or again, the equation is the same. C equals to log of 1 plus alpha I by alpha I pi by sigma square. Alpha 1 and alpha 2 you are substituting over here. Because it's a summation. We are calculating the MIMO capacity is nothing but the sum rate equation that we have already discussed. So we are trying to find out the same. Substitute C log of, so this is just addition. Element wise you can substitute and you get the value as 4.784 bits per second per hertz. That's the capacity, the maximum capacity for the particular channel matrix which is provided to us, given that we have used the water filling optimization algorithm for a MIMO capacity calculation. So two things we have found out quite easily, in fact, that if you are given this question where it will, you might make a problem. It has a two part of it. One part is to calculate the SVD separately, which we have opted out here. So you have to find a way in solving correctly the SVD, and after you have done the SVD, get the value of sigma 1 and sigma 2 or sigma 3, whatever it is, calculate the channel gain. After you have done the channel gain, go back to the basic equation that we have as the optimal power, find a way or find a value of 1 by sigma, that is most important. If that 1 by sigma gives you a result where the allotted power are greater than 0, we are happy with it, whatever be the power, that is not a concern for us, it should be greater than 0. If that is the case, then substitute the same power to find out the sum rate, which should be the maximum rate at which we can send the data over across that particular set of channels. Right? This is a very typical example of SVD and its application to MIMO channel capacity. The second thing, I'll let you know the second part of it, which second type, which might be useful because we are going to follow the same way. So this is a 3x3 matrix. Alright, now this, why it becomes a little tedious in a way, because you have to solve the SVD for a 3x3 matrix. Alright, now for the point over here is that you might come across questions where you might have to do a 3x3 SVD calculation also, or 2x3 also. So you should be ready because the process is same. Process is the same, nothing new about it. But I have taken 3x3 because that is the maximum worst case scenario that might happen. So 3x3, if it is there, the question is again find the MIMO capacity given. PT is given as 0.75. You can see here at the corner I have mentioned. And you have a sigma square which is 3 dB, which is again 2. Same process we are going to adopt, but there is something very interesting that will happen. So as this is a 3x3, naturally we will have power allocated to P1, P2, P3. 3 powers need to be allotted, right? So first step, as you can see over here, I have done the SVD over here. Again, U sigma and V transpose. Considering that you already know how to do SVD, same process needs to be adopted to find this solution. Next is you find the alpha 1, alpha 2, alpha 3. Alpha 1, alpha 2, alpha 2. How? We already know about sigma 1. So this is my sigma 1, sigma 2 and sigma 3. So from there we are trying to find out the same step. Next step, take the optimal power again. So this is again my optimal power. In optimal power we are substituting the data. So we get alpha 1. So now we have P3 powers. So we have P1, P2, P3 equations. So P1, P2, P3 equations. In the previous question, there were 2, P1 and P2. Here, there are 3. Now, in that order, we're trying to find out in the same manner like we have done, and we get a value of 1. This you please understand and note down carefully, or at least understand the concept. So in the same manner, if I go on solving this, we can see P1 plus P2 plus P3 equals PT. Earlier it was P1 plus P2 equals to PT. Here there are 3 powers, so we are adding up. 0.75 is on the right hand side because it's provided to us. We solve them and we get a value of 1 by sigma equal to this. We substitute back to the equations of P1, P2, P3. Okay? Like in the previous case. Now you are understanding over here, see, P1 has a value 0.442, which is valid, which is greater than 0. P2 has 0.37, which is greater than 0. But P3, when we are calculating it, it is coming as minus 0.02. So as per the condition, power cannot be negative. Any Pi cannot be negative. But here you are observing that it is an invalid scenario. Which means the value of 1 by delta which we have chosen is not optimal. Understand the concept? What we are trying to do. So the first choice of 1 by delta, which we have found out, the Lagrangian multiplier, okay, or the ratio of that, in fact, that is not correct because the optimal power is not allotted because in one of the power branch, it is showing as a negative value. So as per the condition, this negative value cannot be there. So it should be approximated to 0. So we take the approximation to P3 equal to 0. Whenever it comes as a negative, you consider that to be a 0 power allotment. So we consider P3 equal to 0. But as P3 equal to now 0, we don't have P1, P2 plus P3 because P3 is 0 now. So we are rewriting the equation once again by only P1 plus P2. Am I clear with this, everyone? P3 we are substituting is 0 because it came as negative from the calculation that we have done. So we have to recalibrate our 1 by lambda. How we are going to do it? We are substituting again the two equations of P1 and P2 and ignoring P3 because we have excluded that from our calculation, keeping that equal to 0. Now we solve again and we get a value of 1 by delta is this. And we substitute to the equations of P1 and P2 and we get a value which both are greater than 0. So what we can conclude now? So now my condition is P1 is greater than 0, P2 is greater than 0 and P3 at least the minimum condition is met that is equal to 0. So these conditions are satisfied. Always remember that whatever happens we need to satisfy the condition. Only then the optimized power should be allotted. So now these are my power allotted 0.3. These are all in linear scale. So you will convert that to dB scale as well. And finally, based on that, we can substitute it in the capacity equation. You can see the same capacity equation. P1, P2 we are calculating over here. P3 we are not considering at all because it's anyway we are considering it to be 0. So it doesn't have much to do with the capacity. So we are calculating it and we are getting a value of 5.23 bits per second per hertz. Considering that there are three set of channels or 3 set of power allotted, which is significantly smaller in that way. 5 bits per second per hertz we are sending. Alright. But the important point is that this is a way in which we are going to solve questions on MIMO capacity calculation or water filling algorithm using the SVD as well as the process of finding the optimal 1 by delta. So just remember one thing, that whatever happens, SVD, if you see a very quick wrap up to this, one very interesting thing that you can see. In this question, do I need anywhere the calculation of U or V? Right. So if you are little bit clever in your approach, you don't need the whole of the SVD actually to calculate. If you can only calculate the value of sigma, that is enough. Am I not right? In this overall Q and VT, this can only be a unfortunate scenario which is not going to come ever, that you have to calculate the SVD as well as do the MIMO capacity and optimal power calculation. It won't come. Okay, so it is expected to be a little bit clever here. The clever is that if you do the SVD, you go on with the calculation, but try to focus more on finding the summation, the sigma, capital sigma calculation. That matrix, if you know, you get hold of the delta 1, delta 2 and delta 3s or whatever it is. Because that is only what you require to find out the optimal power. You don't need U or V. So you can save a lot of time. That's very important. Because you have to optimize the time as well, right? There is also needs to be a water filling mechanism for that as well. So that is one of the way of doing it. So accordingly, you can proceed, find the alpha, get the optimal powers. Just keep in mind that when you substitute everything, you find one of the value of 1 by delta. If you get that, substitute in the equations of P1, P2, P3 or Pz, Pn, how many number of P's we have. If anywhere you are getting a negative value, you should consider that power to be equal to 0. It won't come beyond 3. To be honest, it won't come beyond 3. So if it comes in any one of these is negative, exclude that to equal to 0. Take the same equation with the approximation of the other remaining powers and find a new condition for 1 by delta and then substitute and get the condition satisfied and finally calculate the MIMO capacity. That's all you have to do. Am I clear with this? Simple, right? This is an application of SVD and necessary calculation. So I have done with 3 cross 3. You just look into this material later or try doing it on your own. Take some random H matrix, try to solve and get the results. And I think it will be enough for you. Okay. So this is basically where we end our module of module 6. When we come back post, I guess, Diwali, we don't have classes in between. Post Diwali, when we come back, we'll start with module 3 and module 7 together because those are primarily a continuation to the different generations of mobile communication, how it has evolved and what are the basic architectures behind it. So we'll touch upon specific points when we come back. Okay? Fine.